Right, let's take a little bit closer look at our conics. And first of all, our ellipse, who, as we've seen, eccentricity is less than 1. So I've drawn in the ellipse there. So A being the x-intercepts, B being the y-intercepts. Somewhere inside the ellipse there would be a focus, which I'll label S. And a directrix would be on the outside, so that point of intersection there I'll call Z. Now what we want to do is to come up with an equation for the ellipse. So what do we know? We know the distance from the focus is equal to the eccentricity times distance to the directrix. Now what I do, so S to A would be equal to eccentricity A to Z if I look at the A, but if I look over at A dash, I could also say the distance from A dash to S is equal to the eccentricity times the distance from A dash to Z. So these are two measurements I can work out. If I add them together, right, if you have a look at SA plus SA dash, well basically it's the width of the ellipse. So that would be 2A. If I said SA dash minus SA, and then using the definitions, I could go, well that's eccentricity times A dash Z minus AZ. Now have a look at A dash Z minus AZ, and once again, we get the width of the ellipse. So that's going to be 2A, but times the eccentricity. So basically I've got some simultaneous equations there now. So if I add them together, so twice SA dash will be 2A 1 plus E, so SA, the distance from S to A dash is A 1 plus E. If I subtract them, I get the distance from S to A is A 1 minus E. So the focus would be from the centre, so the origin, to S, but that would be OA minus SA, and we've now worked out an expression for SA, and the distance from O to A is of course just A, and it comes out quite nicely. So the coordinates of the focus is simply AE, the eccentricity times whatever the x-intercept is there. Okay. And actually you have two foci in an ellipse. It's a symmetric shape, so there would be one over the other side as well. So minus AE0 would be the other one. Okay, let's try and work out an equation for the directrix then. So the distance from O to Z, I could say is OA, but plus AZ. Now, OA plus, well if I rewrite AZ using the definition of the ellipse, it would end up being AS divided by the eccentricity, and we've come up with an expression for AS, and OA of course is just A. So let's sub that in, and amazingly we get a very similar expression, but instead of going A times the eccentricity, the directrix is A divided by the eccentricity. So actually quite a simple little way of working it out. You don't have to derive these each time of course. We're just going from scratch to show, hey, this is where it all comes from. Okay, so, and again there would be two directrices, one other side because of symmetry. So one would be x equals plus A on E, one would be minus A on E. Okay, but what about the equation, the actual ellipse itself? We now know the focus is AE0. So that's S. Random point P, we're going to find the locus of P. Basically, what's this equation going to be? The distance from P to S will equal the eccentricity P to N. So I need to know coordinates for N basically. We know N is on the directrix, so the X value is A on E. I'm going horizontal, so it'll have the same Y value as the point P. So we'll get A on E, Y. So SP equals eccentricity times PN. Well, let's just use our distance formula. So subbing into the distance formula, squaring both sides, so we'll get rid of those square root signs. Y minus Y, of course, is 0 on the right hand side there. Y minus 0 all squared is just Y squared. Expanding everything out, and I've grouped them in a particular way. I suppose sort of similar to what we would do with a circle. You know, with a circle we have x squared plus y squared equals something. So I'm grouping the x squareds together, the y squareds together, and everything else I'm putting on the right hand side. So we end up with x squared times 1 minus e squared plus y squared is a squared 1 minus e squared. So if I divide everything by a squared 1 minus e squared, so I've just got 1 on the right hand side, we come up with this lovely expression, x squared on a squared plus y squared on a squared 1 minus e squared is equal to 1. We can make this even neater, because if you look at the y-intercepts, we know the y-intercepts are b. We said they were b. So if I sub that in, we end up with b squared on a squared 1 minus e squared is 1. So in fact, b squared is a squared 1 minus e squared. So I don't have to write it as y squared on a squared 1 minus e squared. I can simply write for an equation, the x squared on a squared plus y squared on b squared is equal to 1. And a and b are the x and the y intercepts. Now, notice there I've put, that's where a is equal to b. So we're talking about one where the foci are on the x-axis. So it would be elongated along the x-axis. So we know b squared is equal to a squared 1 minus e squared. Focus is AE0. Directricity is plus or minus AE. So all these little formulas are going to be handy, because that's the sort of things they're going to ask us. They're going to give us an equation of ellipse and say, what is the focus? What is the directrix? Etc., etc. E, of course, is the eccentricity. But notice I've just rewritten the b squared one. I actually tend to find it a little bit easier this way, where I write it as e squared. I make e squared the subject. Because usually it's the eccentricity you're trying to find. And it's just e squared is a squared minus b squared over a squared. We have what's called a major semi-axis, and we have a minor semi-axis. So unlike a circle where you just have a radius and it's the same in all directions, with an ellipse we say we have a major semi-axis, so it's the longest it can ever be, so that's A, and a minor semi-axis, the shortest it can ever be, and so that's B. Now what happens if it's elongated along the y-axis instead? So B is bigger than A. Now the foci will be on the y-axis instead of the x-axis. What else happens? Oh, the A and the B swap round if you like. So A squared will now be B squared 1 minus E squared. The foci will be 0 plus or minus BE. And the directrices will be y equals, and it'll be divided by E instead of A. So because it's elongated along the y-axis, it's all to do with the y values. So B was the y-intercept. So instead of AE we have BE, instead of A divided by E we have B divided by E. Just the other thing I'll throw in there, a formula which you already know but may not realise it, and that's the formula for the area of an ellipse. And it's pi AB. So pi times the major semi-axis times the minor semi-axis, and I say you know it already because you've been using it for years with the circle. It's just that with the circle they were both the same length, they were both r. So it was pi times r, pi r squared. So in fact the area of a circle is the area of a very special perfect ellipse. So let's do one. So x squared on 9, y squared on 5 is equal to 1. Find the eccentricity, foci, and so on. Now, the first thing I guess to identify is always, is it elongated along the x-axis or the y-axis? Remember, wherever the bigger number is, the bigger number here is with x, so we know it's elongated along the x-axis. That being the case, let's find the eccentricity. We know that A is equal to 3 in this case, because A squared is 9. Eccentricity we said was a squared minus b squared on a squared. B squared would be 5. We have 4/9 is e squared. So eccentricity is 2/3. We should be able to find the other things quite easily now, because the foci is just a times e, so plus or minus 2/0. The directrix a divided by e, we have plus or minus 9 on 2. It then says sketch the ellipse. Now of course you've got your little math aids, I hope, And there's a nice ellipse on there, so you can sort of use it and make the scale fit. I'm going to show you another technique though. I'm not suggesting that you do this every time, but this is actually, if you wanted to draw an accurate ellipse, this is how you would do it. What we do is we draw in what's called the auxiliary circle. Now the auxiliary circle is the circle with the major axis, so in this case 3. Now this ratio becomes important, B over A. So in our case it's root 5 over 3. Because what we end up doing is basically we draw vertical lines. Well, the y-axis is already a vertical line, so that's nice and handy. And I get my ruler and I measure the length of the vertical line from the centre and multiply it by that ratio, root 5 on 3. And that's where I plot the point. So I could draw another vertical line in, measure it, multiply that measurement by root 5 on 3, and that's where I plot the point. I make use of symmetry, because there'll be one on the other side there, plot them, and I can draw as many vertical lines as I like, whatever that measurement is, multiplied by root 5 on 3. And you can see the ellipse starting to take shape. Draw another vertical line in, root 5 on 3, and voila, there would be the ellipse that fits into those dots. So that's how you can draw a really accurate ellipse. Now I'm not suggesting you do that in a test when they simply say, hey, draw the ellipse, but that's how you would do an accurate one. Okay. So I'll just plot in some other important points. There's the foci, the directrices, and that's how I hope you solved that first multiple choice question. When the directrices were on the inside of the foci, that should tell us it was a hyperbola, not an ellipse. Here the directrices are on the outside of the foci. Major axis, now be careful, make sure you answer the question they're being asked. Major axis, we're now saying like diameter rather than radius. So it's not asking for semi-axis there. Major axis would be 6, minor axis would be 2 root 5. Here's one where we're going to have to complete the square. So we've got 9x squared and so on. Well, going to divide everything by 36. 36 being 9 and 4's, what do we call that? Lowest common multiple. That way, on the top of the fractions, I get a coefficient of 1 for the x squared and the y squared, and that makes completing the square easier. So tidying that up, and then the right-hand side, there we go. Amazingly, the right-hand side equals 1. Remember, when we're using these formulae to work out a and so on, the right-hand side has to equal 1. So if it equals any other number, divide by whatever that number is before you do anything. In this case, we're okay. Obviously, we've got some shift happening, just like it happened in the circle. So instead of being at 0, 0, this one's going to be at negative 1, 2, is the centre. Notice b squared is bigger than a squared in this one. So it's elongated along the y-axis. And b is 3. So instead of being a squared minus b squared on a squared, the b's and the a's will swap around. It'll become b squared minus a squared on b squared. You can't get it wrong. Because if you go a squared minus b squared for this one, you're going to end up with a negative number. And so e squared can't be negative. Okay. I suppose it's the bottom of the fraction that you might have a problem with, but you could get that bit wrong. But anyway, eccentricity. Root 5 on 3. So we could work out our foci now, but remember it's shifted. So instead of just being b times e, we've shifted, what was it, up 2 and across 1. So it would be minus 1, 2 plus or minus root 5. The directrices would have been plus or minus 9 on root 5, but again we've shifted everything up 2. So it'll be 2 plus or minus. So from our partel,